Well, the geology field training has a fairly long and involved history within NASA. Uh, it has evolved over 8 years, let's say, something on that order, to a fairly sophisticated and specialized training program. It started out, as you might expect, based largely on the experience that geologists had with training students, normal, generally common students at the university level. And before too much time had passed, it became fairly clear that this was not an effective way to train highly motivated, very intelligent men for the specific task of exploring the moon in a geologic sense. The problem was that over the space of time that you could expose them to geology, it couldn't be concentrated enough so that they would get a fundamental background like normally is given to a university student. It had to be interspaced with many other activities, and there was never any final exam. Nothing that would keep iterating and reiterating the principles that were being taught. And so it was obvious that the normal way of teaching, that is of classes and occasional field trips, was not efficient. It was effective, and it brought it to the surface considerable interest for the field of geology and science in general, but it was not getting to the meat of the problem of exploring the moon in a geologic sense. So we gradually evolved a program where we went out and got I say we, and that's a lot of people were involved in this. I really was only involved for about 3 years, and before I was assigned to 15. But those of us that were concerned about this problem gradually brought into the program some of the very finest professional teachers that we could find at the university level in geology. It turns out these people, as is usually the case with very fine teachers, were also some of the top scientific minds in their particular areas, especially, that we could have found. And the combination was unbeatable. And I'm thinking of people like Leon Silver at Caltech, Dick Johns at Stanford, Richard Johns at Stanford, Bob Sharp at Caltech, Jim Hayes at Harvard. These are the kinds of people that we found who could give the type of geological information we needed in training in the context of what the lunar problems were, help pick the sites so that they weren't, no site on Earth is a direct analog, but that they treated the geometric and philosophical problems that we were going to deal with in geology on the moon. They treated them and again and again re-emphasized them, but in the context of the kinds of operations and the kinds of constraints that a man would be dealing with on the moon. And this turned out to be a much more efficient way to train. Each trip could build on the last trip. We were not only learning procedures, but we were learning geology at the same time. And I think up at the present time, the Apollo Geology Training Program is about as effective as we could make it within the kinds of constraints that we've had to deal with from everywhere else. Now, maybe in a future program where our confidence, having been there, we'll come up with a somewhat different kind of program where we may concentrate our efforts for 6-7 months on training even an experienced geologist in these kind of problems, and then put him on the moon. I think we're eventually going to do that. But it's a question of confidence and understanding. We have to understand what it takes to take a man off the street and put him on the moon. The first step was to take a man off the street and teach him to fly jet airplanes and then put him on the moon after several years of intensive training and understanding of the particular kind of transportation system he had to deal with. The next step very likely will be taking the man off the street, giving him some fundamental physiological training that's I feel confident will be required, and then flying him wherever you want him, whether it's the moon or Mars or around the Earth or what have you. You'll put him there and let him work. And I think that's not too far away. personally, and I think you probably will evolve a different kind of training program. But for the three-man crew Apollo program, I think we finally, particularly for starting about with Apollo 13, but building to more or less a crescendo, if you will, and on Apollo 15 and carrying in through 17, we hit just about the optimum training program. The right people were interested and were working for us and with us rather than for us, and we just produced, I think, some outstanding geologic observers in a short time frame who were capable of more than adequately carrying out the job that was assigned to them, and that was the purpose of the program. The cores are a primary way of sampling the soil cover on the moon, in which lies this history of the sun and the history of any physical process that has affected the surface of the moon. Cosmic rays, solar wind, or changes in the magnetic field of the moon. Those are three major processes that affect the soils of the moon. Now, there are two basic ways that we have, really three, of sampling that soil. One is just with a scoop that I have. I generally carry around when I'm or the LMP carries when he's on the moon, and this is capable of sampling down to, say, 20 to 40 centimeters, depending on how much time you want to spend digging, and you can be fairly selective with it. And so you could sample individual layers down to, say, about that depth. It's fairly time-consuming, but for certain purposes, it's the best way to do it. For one thing is you see the stratigraphy or the layers as you sample them. You can dig a trench and you can sample individual portions and observe and learn while you sample. Now, another technique is the use of some short, what we call core tubes. They're, I guess about, pardon the change of units, but about 16 centimeters long. I've forgotten how exactly what, 16 inches long. I've forgotten how many centimeters right now, and I'm not going to try to calculate it out. Now, these core tubes can be doubled, and they'll get down to a depth, I just remember it, 70 centimeters if you double them. And down to that depth, we again get a very well-preserved sample, geometrically true sample of that 70 centimeters and in a diameter of about 3 or 4 centimeters. And that is probably one of the most valuable samples we have down to that depth. For one thing, at about 70 centimeters, we learned on Apollo 15, you have a minimum temperature zone that's very stable. The ground above it is highly insulating, and that temperature is about minus 20 degrees centigrade, which means it's a cold trap. It means that volatile elements that are moving around within the soil will tend to concentrate there. So that becomes, just by accident, not by design, but it becomes just deep enough to get down to that cold trap, which becomes a valuable thing to do. So we can start to learn about these trace elements, about the lunar atmosphere, about what kind of gases does a planet evolve. The moon is not big enough to hold the gases, but it is almost certainly evolving gases. And we need to know more about that if we're going to understand the origins of our own hydrosphere and atmosphere on the Earth, and potentially the origins of life itself, and what kind of soup did that life begin on Earth. The final technique that we have, or the third technique that we have for sampling the lunar soil, and therefore this solar history book that I think I've referred to, is the deep drill core. Now this samples down to about 3.5 to 4 meters, much the same way as the core tube sample to 70 centimeters or so, except that they do not preserve, the deep drill does not preserve the layers in as high fidelity as do the core tubes. It's a more violent drilling operation, and the diameter of the core is only about 2 centimeters, and so the result is that you get less accurate preservation. It's still preserved, but it's not quite as accurate preservation of the layering. However, you do sample much deeper, and you get that much longer a record. Now, the theory behind all of these soil sampling techniques that we had prior to Apollo 15, and it appeared as if that the theory was very good up to that time with the core tubes that we had. And this theory was that the soil is built up by repetitive impact bombardments, each one of which throws out a little layer of ejecta. And every time it does that, it exposes a new surface to the sun, or to this cosmic rays, or whatever process is affecting it. And these layers build one upon another. And of course, every once in a while, the whole thing is disturbed because another impact comes in and cuts through some of the layers. But in certain places, in places particularly where we call intercrater areas, are in the floors of very old craters that have been there for a long time and you can see have not been disturbed by another impact, you get this continuous superposition of layers through time. Now, we could see that in the core tubes that we took up through Apollo 12, actually up through Apollo 14. Now, when we got the deep drill core back from Apollo 15, all the evidence that we had, both visual and geochemical, by looking at the effects of the solar wind and cosmic rays, indicated that that was a single thick layer, about 3 meters thick, that had been deposited at one time in one event. Well, we had suspected that we had landed on a ray of material, that is a long a line of ejected material from a crater to the north of the Apollo 15 site. We had suspected that, and this, strangely enough, confirmed it. But we still found that we didn't get out of the Apollo 15 core what we expected to, but we got some very significant information anyway. This was the unexpected that I like to refer to, that we got out of the mission. And one of the things was we got a much more complete understanding of the interaction of cosmic rays with the lunar soil, with a relatively undisturbed single unit of debris that was deposited at one time. This is going to pay off not only on 16 and 17 sample analysis, but we can relate back to other samples taken on previous missions now and understand better this cosmic ray history and the generation of isotopes by the interaction of cosmic rays with lunar materials. So now on Apollo 16, we've got another core, and the analysis is not complete yet on that, and I don't know the details. People have been working on it, and I'm not that close to it right now to give you the Apollo 16 data. 17 now, we're going into another different kind of region, and we'll be taking this deep drill core in the dark mantle deposit that covers the landing area. And it may be, if our estimates of ages on the lunar soils are right, on the dark mantle deposit is right, that we will get a core through materials that were deposited during whatever volcanic eruptions occurred to form the dark mantle. Now, these eruptions, where we know about them on Earth, occur in pulses, and so each pulse is another layer out on the countryside. And the ash deposits around Flagstaff, Arizona, or around Pisgah crater in California, or Lunar crater in Nevada, they're layered deposits. And so here we have a chance at 17 to, with the deep drill, to sample 3.5 or 4 meters of these layers if they exist. If it turns out our interpretation is wrong, we'll still sample some depth of lunar soil and whatever lies beneath it. And so we have both potential for the unexpected, but if it turns out the way we expect it to, then we have again a chance to understand how the sun varied and how other things varied, the physical processes varied during the time of these eruptions, which is going to be extremely valuable information to us.
significance of Apollo 17 to us, to the crew, is probably best summed up in the meaning of our patch as we designed it and as the ideas that we put into it. We felt certainly that Apollo 17, in spite of the fact that it's the last flight in the Apollo program, is really not the end, but rather the beginning. It's sort of a conclusion of the culmination of what we consider man's greatest achievement, certainly in our lifetime. And looking in the future, these achievements and the potentials of them have literally no bounds. So we have a bust of Apollo, of the god of Apollo, on our patch. He represents not just Apollo, the Apollo program, but we feel that he represents, in the figure that he gives us on our patch, mankind himself. Represents knowledge, represents wisdom. And Apollo is looking out into the future. He's not looking behind. And he's not simply looking at the moon, someplace that mankind has been, and in a sense has a goal that mankind has accomplished. But he's looking on beyond the moon and into the future. We have, along with him, up in the corner of our patch, a golden moon, sort of representing a golden era of space flight that we are bringing to a close now. Superimposed upon this moon, and alongside the bust of Apollo, alongside mankind, we're a little bit parochial. We have a very contemporary American Eagle whose wings are colored with the blue and covered with the red stripes of our flag, and we have 3 white stars indented into the top of this eagle's wings. And the significance there is to remind us, not just in this country, and as I say, parochially speaking, the rest of the world, that the achievements that have happened in this past decade were not by accident. America brought us where we are today, and the United States of America is going to lead us into the achievements and the accomplishments of the future.
I feel the prime mission objective is the continued Apollo exploration of the Earth's frontier in space, which presently is at the moon. And that entails many sub-objectives. Most important of this particular phase of lunar exploration is the surface activities, where we are trying to characterize or continue the characterization of the lunar surface. And also, secondly, the regional characterization of that surface from orbit using a variety of remote sensing equipment, as we call it. We've been training for about 12 months, maybe slightly longer than that. It's hard to remember once you get involved in this thing how long you've been working on it. But of course, the training for any spaceflight mission begins several years before that. And for me, I guess the concentrated training for spaceflight began with Apollo 15 in the December of 1969. Site selection in all the missions has been a fairly long and drawn-out process. It entails utilizing, or the utilization by NASA, of a number of scientific advisory groups and the inputs of many individuals across the country, scientists primarily. The Taurus littoral site in the northeastern part of the moon, at the edge of one of the large lunar basins called Serenitatis, was selected primarily as representing both a new part of the moon, which we had not explored yet, and having 2 major features that would allow us to hopefully complete, as near as that is possible to do, this first phase of lunar exploration. Those features are the edge of the Serenitatis Basin, which is exposed in some 6,000 to 7,000 foot mountain fronts, where we have a very strong possibility of finding some of the oldest, if not the oldest, rocks that have so far been sampled and observed on the moon. And it also has, appropriately I think, the dark mantling deposit that is potentially some of the youngest volcanic rocks that we've seen on the moon, possibly even less than 1 billion years old. Now, this makes it appropriate, as I said, because it gives the last mission the role of filling in the first and last chapters of a lunar history book that Apollo has the capability of writing. And I think we'll find it very exciting for that reason, and I think the scientists who helped select the site, maybe not entirely consciously when they selected it, but have picked an excellent site for the last Apollo mission to the moon. Well, it's somewhat difficult to discuss the specifics of the site without building some background in what we're really after on the moon. Let me start, if I may, and this may seem to digress a little bit, but let me start, if I may, with the major purpose, scientific purposes that we have for exploring the moon, and then I'll try to answer your question specifically. The major purposes I look at, are threefold. Scientific now. We, of course, have many other objectives for lunar exploration than the scientific ones. But the scientific objectives are, one, to understand the history of the moon as it relates to the history of our Earth in particular and to the solar system in general, of which our Earth is part of. Now, by relating that history to the Earth, we have a chance, and we suspected this before we ever explored the moon. We now know it that it is specifically true, that in the moon we have a window into the very early history of a planet in the near-Earth part of the solar system. That is a history which is almost totally obscured to us on Earth. The history from 3.3 billion years ago back to the beginnings of the Earth, say 4.6 billion years ago, is practically obscured completely on the Earth. On the moon, that's where lunar history starts, and that's why it's exciting to Earth scientists who have for years been trying to find out what happened to the Earth in that very early time. So the moon's history that we have studied so far, its ancient history, begins at about 3.2 or 3 billion years ago, and we have carried it back, we feel, about to 4.1 or so. So we're getting close to the beginnings of the solar system, and therefore the beginnings of our Earth, and an understanding of the processes that really affected the total distribution of materials on the Earth that we now are trying to study through the mask of recent geologic processes. And it's in those materials that lie our resources, and in the long-term understanding of the Earth so that we can exploit those resources, and exploit them in obviously a now, I think, a much more enlightened way than maybe we did in the past, but nevertheless we must exploit them in order to preserve the civilization we're used to. With understanding the moon, and we're not nearly far enough along now with the Apollo program, but we've made a start. And with that understanding, we now can start to think about, okay, how did that early history of the Earth affect the distribution of resources? That's reason number one. A little bit involved, but it is probably the primary material justification, scientific justification for going to the moon. Secondly, and equally important related to the Earth, is an understanding of the history of the sun. And within the soils of the moon, and within the rocks of the moon, the very surface layers of the moon, we are starting to see the effects of solar history on those materials. And there is no way we can get this information on the Earth or in orbit around the Earth, because what we see there is what's happening now. What we see on the moon, we can go through the record of the soil and see what has happened 100 million years ago and up to probably at least 1 billion years ago in some places on the moon. So, and if we don't understand the sun and how it affects materials and what the history of that sun has been as it has affected our own environment on Earth, it's going to be very difficult to understand how to control and how to preserve the environment that we now know, because the sun is still the prime mover, the prime force for change in the environment we have to deal with. So it's very difficult to get specific on what individual pieces of knowledge that we've gotten out of the moon or what we will get out of the Skylab program when it flies, which will study the present-day sun. It's difficult to be specific, but it's this total knowledge about the sun that is so critical in understanding our own environment that we're after. Now finally, as in any major exploration program, whether it was the exploration of the American West or the exploration of Antarctica or now the exploration of the moon and the planets in general now, it's searching and expecting to find the unexpected. And that is really almost invariably what turns out to be the major payoff. We won't know it for 50, 100 years, but some of the things that we are finding and will find that were completely unexpected, that we didn't plan to find, will almost certainly be the most important things in the eyes of the history of science, and very probably in the eyes of history of man.